Now, in human system, metal oxide venture through breathing, gastrointestinal tract, and skin, and then they circulate via blood or lymphatic system, and they can accumulate in various organs. Reactive oxygen species is one of the major gateways through which metal oxide nanoparticles can exhibit their toxicity. They can modulate DNA strands and further leads to other ways of cell death, including autophagy and apoptosis. Considering the complexity of nanoparticles and their diverse applications to mankind, it is important for us to determine their expected toxicity, and this should be done quickly and more economically. And that's why we need to use alternative methods, including in silico techniques. So these predictions, in silico predictions, can be used to prioritize metal oxides for their toxicity and further testing. Behind QSA, behind read across, which is similar to QSA. So read across is a prediction method of unknown chemicals from chemical analogs with known activity or toxicity from the same chemical category. So the target compounds should be similar to the source chemicals. The similarity may be in terms of their structural features or their physicochemical properties. And read be used for data gap filling. So defined chemical category is required for use of redact one-to-one prediction, one to many, many to one, and many to many. So in general, they are of two types. There are two categories of read across. One is the analog approach, another is category approach. In case of analog approach, we have limited number of compounds. So maybe based on the single compound or very limited number of compounds, we can predict activity or toxicity of the target chemicals. So from a class of compounds, we can predict compounds. So this is our source compound, and this is our base. So as their close activity or toxicity pattern will be also similar. In case of cation, based on the number of compounds, we can predict activity or a target compound is within the chemical space, and sometimes we can do extrapolation that is beyond the chemical space. This is out of range of the chemical space. Still, we can extrapolate the activity or toxicity compounds, and there may be some outliers also. They are beyond the range. Now, what do we mean by similarity? Now, as I mentioned, the similarity is expressed in terms of the chemical features, and we represent our chemical compounds through various graphical representation, which may be two-dimensional or three-dimensional or higher dimensional. And presentation, and from that we can gather information about numbers are actually descriptors. So descriptors are numerical typical descriptors, and descriptors may be obtained at different levels. They may be when compound structure by using some information like how many carbons present, or how many carbon are present, or how many carbon atoms, or we can say how many rings are present, or how many carbonyl rings, carbonyl groups are present, or how many heterocyclic rings are present. So this may be some kind of information, or we can derive the information from physiochemical experiments also, like say the properties of the compounds through experiments, like say acidic dissociation constant and so on. So this kind of information also depicts some kind of features about the structures. You can use different bond angle, torsion angle, etc. And we can use the conformational aspects also. So based on the structural features and dimensions, so they can be 0D, like say constitutional descriptors, say number of carbon atoms or number of nitrogen atoms. These are constitutional descriptors, so 0 dimensional. Or they may be 1 dimensional. So these are substructure based, or maybe fingerprints also. So many indices like say branching index of Kier and Hall. 3D descriptor based on the 3-dimensional representation. It may be 4D, where we also include the conformational aspect, and there will be higher dimensional descriptors also. We can include the newer constraints in during descriptor calculation. But in all cases, the structural features are converted into numerical form. And once we get these numerical values, we are able to do some kind of numerical manipulation. We can apply different feature selection strategies to know which features are actually important for us, because all these numbers are not important for us, but some of them are important for the particular endpoint. And then we can apply some kind of tool or machine learning algorithm, regression based or point data in quantitative form. Then we can use regression based, because that will give exact prediction of the endpoint data. But when we have graded values, that is like toxic or non-toxic, or active or inactive, in those cases we do not have exact quantitative values, so we cannot use regression. In those cases, we will use classification. So it may be binary classification, like classification between two classes, active and inactive, etc. And then we'll have some kind of model, and that model can be used for prediction purpose after appropriate quality checking and validation. So this is the flow of any kind of structure activity in quantitative form. So say these are some of the compounds: ethyl benzene, nitrobenzene, chlorobenzene. Here only 3 examples are shown just to save space and for the ease of understanding. But usually we will have a number of compounds, and we will have a list. So for each compound, we'll be able to calculate some kind of descriptors. Like say here, some simple descriptors are shown: number of carbon atoms, number of nitrogen atoms, number of oxygen atoms, number of chlorine, number of double bonded O, and so on. So we'll have some kind of values here. There we may have molecular weight also as one of the descriptors. So we can have in this way descriptor matrix. And also we'll have one more column, that is the activity column, that we are going to model, because we want to uh,